So far in this course, the only rendering technique we've looked at is rasterization, where geometry is projected in a way that's appropriate for viewing on a 2D plane. And then a simple material model is used to determine the shading. The sort of shading we can simulate with only this direct illumination is really quite limited, as only a single bounce of light can be used, right? Recall that simple diffuse and specular shading is calculated using dot products between pairs of vectors, resulting in surface shading caused by only this single bounce of light. Additionally, shadows have to be deliberately added in as they're not created naturally by this process. So all in all, direct illumination in and of itself provides a fast simulation of how light generally behaves and is great for real-time applications. However, this method trades realism for speed, and historically has not been sufficient to render scenes realistically enough for film or VFX. This is where ray tracing comes in and allows us to simulate the behavior of light in a far more realistic way. Note that the real-time ray tracing made accessible in game development in the late 2010s is a result of specific advances in GPU technology. Ray-traced games do not solely use ray tracing to render frames, however. Instead, frames are first rasterized as a low-cost starting point, and then ray tracing technology is utilized to augment the appearance of the frame. It's important to make this distinction, as it would be incorrect to say that the same process happening in an offline ray-traced render, like in Arnold or Cycles, for example, is the same as what's happening in a 2020 AAA game title. So we've seen how rasterization is an object-centric approach, where for each object in the scene, we project geometry onto a plane and see if the surface area covered by a pixel is visible to the camera. With ray tracing, on the other hand, we take the opposite approach, and instead iterate through each pixel of the final image we wish to construct and cast rays out into the scene. Now, for each object, and therefore polygon, that this ray intersects, we determine what geometry is visible and therefore how the pixel should be shaded. In contrast to rasterization, we could call this a pixel-centric approach to rendering, since we're iterating through every pixel in the final image and casting one ray per pixel to figure out how that pixel should be shaded. To be truly accurate to reality, the rays would be cast from light sources and traced to see if they reach the camera, right? This is how light works in the real world. Light obviously comes from a light source and is simply perceived by either a camera or our eyes. This would be called forward ray tracing. However, it's quite inefficient to render a final image this way, as we'd have to cast many rays from a light source, which will never reach the camera and therefore contribute to the final image. To ensure that we're rendering the scene in the most efficient way, we generally trace rays from the camera to the light source. This is the traditional approach to ray tracing and is called backwards ray tracing, since it reverses the true-to-life approach. Now, it's worth noting here that there often is some confusion in the terms, with forwards and backwards ray tracing sometimes being reversed due to the fact that camera-based, or what we're going to call backwards ray tracing, was the first ray tracing method used historically. But anyway, for clarity, we're going to ignore the historical confusion here, and we're just going to stick to the definitions of camera-based ray tracing being backwards ray tracing, and light-based ray tracing being forwards or true-to-life ray tracing. In backwards ray tracing, we cast a ray from the camera's origin through a pixel of our target image plane. We then perform line-plane intersections to see if the ray intersects with any object, and of course, therefore polygon, in the scene. And this is where ray tracing starts to give us some nice, interesting effects that can't be achieved with direct illumination alone. After a ray intersects with a polygon, we can spawn more rays from here. We'll likely want to determine if the surface point is in shadow, so a shadow ray is cast towards the light source. If that ray reaches the light source, then there's no shadowing, and we can just use a direct illumination model to get diffuse and specular shading for the surface point. If it is obstructed by other geometry, then we'll know that that surface point is in shadow. If the surface material is reflective, like a mirror, then we'll be able to spawn off a reflection ray as well. If the material is transparent, we'll have yet another ray created, this time for refraction. With this recursive approach to spawning new rays, we can accumulate information from all the spawned rays, each of which contribute to the final pixel color. We've seen that ray tracing is a pixel-centric rendering technique, and that means we need to be testing if the ray cast into the scene for a given pixel intersects with any polygon in the scene. Even with 100,000 polygons in the scene, which really isn't much by modern standards of complexity, this means that 100,000 line intersections would need to be performed per pixel. And this is wildly inefficient given that only one of those intersections is the one we're actually looking for. So we optimize the process primarily through the use of what we call bounding volume hierarchies. With bounding volume hierarchies, we group objects and polygons that are close to one another and surround them in their bounding volume, or bounding box. Sets of bounding volumes are grouped together within larger volumes, and so on, until the entire scene is enclosed in a single volume. The hierarchical nature of this organization makes it possible to efficiently decide where to focus our rendering efforts for a single ray. If a ray intersects a bounding volume, it will only be possible for that ray to eventually intersect a polygon somewhere within that volume itself. The same is true of every successive intersection within a bounding volume, eliminating large regions of geometry which don't even need to be tested. Eventually, we reach the lowest level bounding volume, and each triangle inside that volume is tested against the ray. Sure, it's still multiple line plane intersections, most of which are going to be irrelevant, but it's still a lot fewer than the number of intersections that we need to test if we had to do this without bounding volume hierarchies. We'll look at one other ray tracing based procedure before we finish off this lecture. Ultimately here, our goal is going to be to get to the topic of global illumination and how ray tracing can be used to simulate the effect of light bouncing around the scene and indirectly illuminating surfaces. But before we get to that in the next lecture, we'll first discuss ambient occlusion. Ambient occlusion, which is commonly abbreviated as just AO, is a non-physically accurate, but still plausible, approximation of how occluded geometry tends to be darkened when under the effects of global illumination. AO operates simply by sending out a burst of rays in a hemisphere over every relevant surface point in the scene. If some of these rays intersect with geometry, then the surface point will be darkened because of the proximity of geometry, which in real life would obstruct some of the light traveling towards that point. Again, while it's not entirely realistic or physically based, the effects can be quite effective and cause cracks, crevices, and areas under objects to get nice, soft, dark shadows, while surface points that are out in the open remain undarkened.